Hello everyone, I'm Paul and today we're solving problem 3432, count partitions with even sum difference. This is easy, so here I will show you my thought process and efficient solution. We are given an integer array nums of length n, so let's say that this is the array. I'm going to return the number of partitions where the difference between the sum of the left and right subarrays is even. First, let's see what a partition is. A partition is an index that splits the array in two subarrays, such that the left subarray goes from index 0 to I, and the right subarray goes from I plus 1 to n minus 1. So, for example, if we take this index for the partition, the left subarray goes from 0 to this index, and the right subarray goes from I plus 1, meaning from this index, to the end of the array. I'm going to return the number of partitions where the difference between the sum of the left subarray and the right subarray is even. For example, with this partition we get these two subarrays and the sum here is 20 and the sum here is 16. The difference between these two is 4, and given that this is even, this is a valid partition. Now, how can we check if this number is even? Well, we can do this modulo 2, and if the result is 0, this means that this number is even. If it's 1, it's odd. So for this example, the result is 4, meaning this is a valid partition. This is also valid, this is also valid, and this is also valid. Those are the 4 valid partitions. Now maybe you are thinking about iterating every element in this array from left to right. So first the I pointer is here, and we are building a partition with the I index every time. The left subarray goes from 0 to I, so this is the left subarray in this case, and the right subarray goes from I plus 1 to n minus 1, so this is the right subarray. And every time you might be thinking in iterating the corresponding indices for the left subarray and the corresponding indices for the right subarray. So you could have some variables such as sum for left, which is initially 0, and the sum for right, which is initially 0. And you can use the shape pointer to iterate every index in this left subarray. First we have a 10, so we add 10 here. And now you could iterate every element in this right subarray from the first index. So here is the shape pointer. First we have a 10, so this is 10. Now we have a 3, so this is 13. Now we have a 7, so this is 20. Finally we have a 6, so this is 26. And finally you can get the difference of left and right, and 26 minus 10 is 16. And given that 16 modulo 2 is 0, this means that this is an even number. So this is a valid partition. At this point, you can add 1 to the result. So next, the I pointer is here, and you can repeat the exact same process. This is the index for the current partition, so the left subarray is this, and the right subarray is this. You can take the sum of each of these, check what's the difference, and if it's even, you add 1 to the result, you update the I pointer, and you repeat the same process until you reach the end of the array with this I pointer. That's how you reach number 4, and this is the result for this input. Now for each of these elements, we are iterating the entire array, so this requires big O of n squared time complexity. And here n can be up to 100, and 100 square is not a very big number. We can handle this, so this solution will work. But this is actually not very efficient. So I want to take this opportunity to show you a solution that's more efficient, that runs in big O of n time complexity, and this will be useful for future problems. And for this we are using something called prefix sum. So let's see how this works. Let's say that we have a new array of this same length. And we are iterating every element here to fill this array. We are storing in each of these elements the accumulated sum in this array up to every corresponding index. So first we are at this index and we take the accumulated sum up to this point, meaning 0 plus the current value. And 0 plus 10 is 10. Next we are here, so we take the accumulated sum plus the current value, and 10 plus 10 is 20. Next we are here, so we do 20 plus 3, 23. Next here, 23 plus 7 is 30. Finally here, 30 plus 6 is 36. And now let's say that we are trying to get the sum of this subarray in big O of 1 time complexity. How can we do this with this array? Well, we can take the sum of every element up to this right element, meaning we take this prefix sum and subtract the sum of every element up to the left bound for this subarray minus 1, meaning here. So we subtract everything up to this element. We take this prefix sum. That's how we get this subarray, which is exactly what we want up here. So we need to do 36, meaning the right bound, 36 minus the left bound minus 1. And 36 minus 20 is 16. So the sum of the elements in this subarray is 16. And we are doing this lookup in big O of 1 time complexity, which is very efficient. And here we are also using something called suffix sum, which, as you might guess, it's exactly the same as prefix sum, but we are going in reverse. Let's say that we have an array of this same length, and every time we store in every index the corresponding sum, the accumulated sum, up to this index plus the current number. So the accumulated sum up to this moment is 0 plus the current number is 6. Next we are here, and 6 plus 7 is 13. Next here, 13 plus 3 is 16. Next here, 16 plus 10 is 26. Now here, 26 plus 10 is 36. So let's say that we are trying to get the suffix sum of these three elements. Well, we can take the left bound, meaning we take this, and subtract the right bound plus 1, meaning we subtract this. And 36 minus 13 is 23. And this is the sum of the elements in this subarray. So now with this information, how can we solve this efficiently? Well, we can iterate every element from left to right, so the I pointer is here. And we will have two variables, left and right. Left is initially 0, and right will be the total sum of these elements, meaning 36 in this case. So this will be our prefix sum, and this is our suffix sum. First we are here, and every time we want to add the current element to the prefix sum, 0 plus 10 is 10, and subtract this from the suffix sum. So this is 26 now. What this represents is that the left subarray has a sum of 10 and the right subarray has a sum of 26. And now we don't have to iterate every element in each of these subarrays. We can do this in big O of 1 time complexity, which is very efficient. So the difference between these two numbers is 16, and 16 modulo 2 is 0, meaning this is even, so now we add 1 to the result. Now we are here, so we add 10 to the prefix sum, this is 20, and subtract 10 from the suffix sum, this is 16, meaning the left subarray has a sum of 20 and the right subarray has a sum of 16. So now the difference between these two is 4, and 4 modulo 2 is 0, so this is even. We add another 1 to the result, and this is 2. Now the I pointer is here, so we add 3 to the prefix sum, this is 23, and subtract this from the suffix sum, so this is 13. The difference between these two is 7, 8, 9, 10. And this modulo 2 is 0, so this is even, we add 1 to the result, and this is 3. Finally, here we add 7 to 23 and this is 30. We subtract this from 13 and the result is 6. The difference between 30 and 6 is 24 and this modulo 2 is equal to 0. So this is even. We add another one to the result and this is 4. Now we update the I pointer and we end the loop here because we can't form a right subarray because it goes from I plus 1 to n minus 1 and I plus 1 is out of bounds here. So we end the loop here and return the result 4. And now this is very efficient. We are solving this in big O of n time complexity and space complexity is big O of 1. So with this in mind, now let's go with the code. First, n is the length of nums, result is initially 0, left is 0, and right is the sum of nums. Remember that this is the prefix sum and this is the suffix sum. Now for every index in the range from 0 to n minus 1, remember that this is non-inclusive, so we are skipping the last element. Every time we want to add to the prefix sum the current number and subtract from the suffix sum the current number. And now we are checking the condition of the problem if left minus right modulo 2 is equal to 0, we add 1 to the result. And finally return result. So let's submit this. As you can see, this works and it's very efficient. So if you found this useful, please drop a like, subscribe, and see you in the next one. Bye bye.